IEEE 802.4 standard describes a local area network architecture that is often used to implement factory automation networks. With the token bus standard, control of the transmission medium is determined by possession of a special frame called the token that is transmitted from one station to the next. Only the station that currently has the token is able to transmit. The network takes the physical form of a bus, but the way in which the token is passed from station to station logically implements a ring structure. The token bus standard employs a similar logical model as the other medium access control standards. As with the other IEEE Project 802 standards, the OSI data link layer is divided into a logical link control sublayer and a medium access control sublayer. Below the MAC sublayer is the physical layer. The standard also defines the characteristics of the physical transmission medium, called the trunk cable, the trunk coupling unit, used to tap into the trunk cable, and a drop cable, used to attach the LAN adapter to the trunk coupling unit. The IEEE 802.2 standard defines the logical link control sublayer. IEEE 802.4 defines the components below logical link control. The primary functions that the medium access control sublayer performs are interface to the LLC sublayer, token handling, ring maintenance, fault detection and recovery, and sending and receiving data. Each of these major functions is discussed next, beginning with the LLC interface. A major function of the MAC sublayer is to provide services to the LLC sublayer. On the sending side, the MAC sublayer receives protocol data units from the LLC sublayer and prepares them for transmission. On the receiving side, the MAC sublayer accepts frames that are addressed to this station and passes them up to logical link control. The token handling function includes passing the token from one station to the next, recognizing a token when it is received, and optionally providing for the prioritization of protocol data units. For ring maintenance, the logical ring that the stations form needs to be initialized when the network is powered up and modified as stations are added or deleted. For fault detection and recovery, possible faults that must be detected and, where possible, corrected include multiple tokens, lost tokens, token pass failures, stations with inoperative receivers, and duplicate station addresses. For sending and receiving data in a sending station, the MAC sublayer adds protocol information to the LLC PDU it receives to create a MAC frame and passes the frame to the physical layer for transmission across the network. In a receiving station, the MAC sublayer accepts each frame from the physical layer and strips off the PCI to recreate the original LLC PDU. The token bus form of medium access control is based on a short MAC control frame called a token that is passed in a logical sequence from one station to the next. The token represents the right to transmit. When a station receives the token, it starts a timer and is allowed to transmit protocol data units until it has no more to send or until the timer expires. The station then transmits the token to the next station. If the station that receives the token has PDUs to transmit, it starts a timer and transmits its PDUs. Each station is given the opportunity to transmit for a predetermined length of time, each time the token circulates around the ring. The time limit prevents a single station from monopolizing the network. When the station's timer expires, the station passes the token whether or not it has more PDUs to send. Stations that have no PDUs to transmit pass the token immediately to the next station. The token is passed from station to station in descending order based on station addresses. When the station having the lowest address value is reached, that station passes the token to the station having the highest network address. Because the physical topology takes the form of a bus, the token and all other frames are sent in a broadcast fashion and are received by all stations on the network. Every frame contains a destination address field that identifies the station or stations that are to receive it. Each station then accepts and processes only frames that are addressed to it. A station passes the token by changing the address field in the token to that of the next station on the logical ring, and then transmitting it into the network. Only station 42 accepts it. Since a station transmits only when it has received the token, two stations should never transmit at the same time and should never interfere with one another. Therefore, there is no minimum length requirement for frames, and the token can be very short. Token transmission accounts for a very small percentage of the channel capacity. In order to control the operation of the logical ring, each station must know, in addition to its own address, the address of its successor, the station to which it transmits the token, and its predecessor, the station from which it received the token. As stations are added to or deleted from the ring, stations must update their predecessor and successor address values accordingly. These same procedures are used when the network is first initialized. Suppose station 37 wishes to be deleted from the ring so it can power down. It waits until it receives the token. It then sends a set successor frame to its predecessor, station 42, notifying it to change its successor address to station 22, station 37's successor. It then sends the token, as usual, to station 22. At this point, station 22 still thinks that its predecessor is station 37, the station that has just been removed from the ring. Each frame that is transmitted, including the token, contains both a source address and a destination address. After the next token rotation, when station 22 gets the token, it knows that it received the token from station 42 instead of station 37, so it updates its predecessor address to station 42. Station 37 has now been deleted from the ring. In order to allow for stations to be added to the logical ring as they are powered up, each station must periodically invite new stations to join the network. Station 37 comes back online and waits to be invited to rejoin the ring. A station invites new stations to join the ring each few times that it receives the token, governed by a system variable as long as traffic is light. Station 42 does this by transmitting a solicit successor control frame after it has received the token and has determined that it is time to do ring maintenance. The solicit successor frame contains the station's own address and the station address of its current successor. Station 42 then waits a period of time called the response window to see if any station responds. The response window is equal to the slot time, twice the end-to-end propagation delay of the transmission medium plus the station delay time. If the token holder detects no response during the response window, it assumes no new station wishes to be added to the ring. If the token holder detects a response from a station that wishes to be added to the ring, like station 37, it checks to see if that station's address is within the range specified in the solicit successor frame. Station 37 is within that range, so station 42, the station that sent the solicit successor frame, changes its successor address to be that of station 37 and transmits the token to station 37. Station 37 then sets its successor and predecessor addresses appropriately and proceeds to process the token. When station 22 receives the token from station 37, it replaces its predecessor address with station 37's address. The IEEE 802.4 standard describes a form of token passing in which stations are arranged in the form of a logical ring on a bus-structured network. You have seen the IEEE 802.4 logical model, the functions of the MAC sublayer, a demonstration of the Token Bus Medium Access Control Protocol, and examples of logical ring maintenance procedures. Please turn to Mini Course 1 in your personal reference guide and continue your study.